Countless chemical reactions are taking place in living organisms and in the non-living environment, and these are happening at different rates. The study of the rates at which reactions take place is called chemical kinetics. Scientists can make use of the results of these investigations to increase or decrease the rate at which some chemical changes are taking place in various endeavors. Number 1, to treat some types of diseases. Some drugs could be tailored to block the active sites of some enzymes to slow down their activities to achieve some beneficial outcomes. One method of treating erectile dysfunction makes use of enzyme blockers. Other types of diseases such as diabetes and HIV are treated in similar ways. The rate of growth of some strains of bacteria is slowed down by the use of antibiotics. Number 2, to increase productivity for some industrial products. To increase the rate at which ammonia is produced, for example, certain conditions of temperature, pressure, and specific catalysts must be used. Number 3, to reduce environmental pollution. Motor vehicles with combustion engines and industries use catalysts to ensure that dangerous effluents are reduced to harmless substances before they are released into the environment. For example, platinum and palladium catalysts are used as converters that change dangerous nitric oxide, nitrogen dioxide, and carbon monoxide to harmless nitrogen and carbon dioxide before they exit the tailpipes of these vehicles. Chemical kinetics can enable scientists to understand how the mechanisms by which reactions happen at the molecular level. The knowledge of these reactions mechanisms can be used to regulate the rate of these reactions, again, for some beneficial outcomes. Measuring reaction rates. At the very beginning of a chemical reaction, its rate is the greatest. However, as time elapses, its rate decreases. The following table gives the results of how the concentrations of reactant A and product B change with time. In this reaction, a compound A is being changed to a different compound B. This table shows the change in concentration of reactant A as it disappears, and the change in concentration of the formation of product B. For the first 3.5 seconds, the reduction in concentration of A is 5.2, since it changed from 7 moles per liter to 1.8 moles per liter. During the same time period, the change in concentration in the formation of B is 5.2 moles per liter, since it changed from 0 to 5.2 moles per liter. For the next 7.25 seconds, that is the difference between that time there and that time there, the reduction in concentration of A is 1.8 moles per liter, because it is changing from 1.80 moles per liter to 0. For this same period of time, the increase in concentration of B is 1.80 moles per liter, since it changed from 5.20 moles per liter to 7.00 moles per liter. Calculating average rate of a reaction. The average rate of a reaction is a change in concentration of either a product or reactant for a given period of time. The change in concentration is given in notation delta C, and the time period for which the change takes place is given in notation delta T. And generally speaking, this is the way of representing how the average rate of reaction can be calculated. You're going to see R with an AV written as a subscript there. We'll first of all show how we can use a product to calculate the average rate of a reaction. And the product that we'll use is that of the one that is formed in the reaction above, B. So we'll do the average rate for the first 3.5 seconds. For the first 3.5 seconds, the change in concentration of B is 5.2 moles per liter. Substituting those values into this expression here, that is it for the change in concentration, and that is it for the time, we got 1.49 moles per liter per second. So this is the average rate for the first 3.5 seconds. For the next 7.25 seconds, let's look at the concentration change for B. So the difference between this time here and this time here is 7.25 seconds. And the change in concentration is 1.80 moles per liter, since it is changing from 5.2 moles per liter to 7.00 moles per liter. Substituting those values into that expression there, where that is your delta C and that's your delta T, this is what is obtained, 0.248 moles per liter. Now we'll use the reactant to calculate the average rate, and we'll use the reactant A to calculate the average rate for the first 3.5 seconds. And again, if you go back to the table, for the first 3.5 seconds, the concentration of A changed from 0.00 moles per liter to 1.80 moles per liter, and that's the difference there. That's your delta C. Substituting those values into the expression, but there's a catch here. Because we are subtracting a large number from a smaller number, we will end up with this negative sign here. Go back to the table and let's see that. To find our delta C, we have to take the final concentration, which is this, and subtract the initial concentration of that, and that is why we ended up with a negative value here. But rates must always be positive. So the point of emphasis is this. Whenever we have this expression here for calculating the average rate, when we're doing it for a reactant, a negative sign is placed in front of that expression here to negate this negative sign here. As we have done here, you find now instead of ending up with this negative sign here, we ended up with a positive sign. So always remember that when a reactant is used to calculate the average rate of the reaction, a negative sign is placed in front of the expression there, such that that negative sign which would have been produced is negated, so our answer is always positive. So the change in concentration of A and B are plotted on this graph here. These two lines are produced. This one here will represent the formation of B. You can see how B is increasing in concentration because it is a product, and you can see that A is reducing in concentration because it is a reactant and is being consumed. You can see that the rate of production of B is commensurate with the rate in reduction of A. Second point, I want you to look at how you can use this graph to calculate the average rate for these two segments here. For the first 3.5 seconds, by taking the rise here, which represents the change in concentration, which is moving from 0 to 5.2, and then you take the time here, which is 3.5. Doing that, take the rise and divide it by the run, that gives you the average rate. It is 1.49 moles per liter per second. Doing the same thing here for the next 7.25 seconds. This is moving from 3.5, okay, to 10.7 here. So take your rise here, which is 1.8, and divide that by the run here, which was 7.25. We ended up with a slope here, which represents the average rate for the next segment. Notice what happens. The rate of a reaction slows down with time. And later on you're going to find that that is attributed to a change in concentration of the reactants. We now have to distinguish between instantaneous rate and average rate. Let us suppose that a product B was being formed and is represented by this green line here. We could have found the average rate for the first 2 seconds by dividing the change in concentration, which is delta C, which you could have gotten from this graph. We could have found its average rate by finding the slope of this line. And that is done by taking the rise here, which represents a change in concentration, over delta T here, which is called the run, which represents a change in time. And that would have given us, like we did before, the average rate for this segment of the reaction there. However, if you wanted to know the instantaneous rate at a particular time, say this point here, we find the slope to the tangent at this point here. So you draw a tangent to this point here, and you find the slope of that by taking the delta C here over its delta T. So this is how the instantaneous rate for a reaction at any particular time can be determined as opposed to an average rate. As an exercise, you can find the instantaneous rate at that point. You can look at a little sample problem here. Here calcium carbonate is reacted with hydrochloric acid according to this chemical equation. They produce a solution of calcium chloride and water, and carbonous gas is liberated. If the concentration of CO2 changes from 0.000 mole per liter to 0.00 mole per liter over a 20-second period of time, you're asked to find the average rate of formation of carbon dioxide for that period of time. Of course, you take delta C and you divide by delta T. And your delta C will be equal to that value minus that value here, which is equal to that. And that's your delta T here. And that's your rate of change for carbon dioxide. Consider the following reaction, where permanganate ions are reacted with iron 2 ions in the presence of an acid to produce manganese 2 plus ions, iron 3 plus, and water. Measuring the rate of this reaction can be with regards to any one of these three reactants here, or any one of these three products. A causal observation reveals that the relative rates of consumption of these reactants are governed by their mole ratios. For every 1 mole of permanganate ions that react, 5 moles of Fe2 plus ions must react along with 8 moles of hydrogen ions. And the same thing can be said of the products. For every 1 mole of Mn2 plus ions that are formed, 5 moles of Fe3 plus ions are formed, and 4 moles of water are formed. So if the rate of formation of one product is measured, the rates of formation of the others will be different according to their mole ratios. The same can be said of the rate of consumption of any reactant. So here's a problem. The experimentally determined rate of formation of Mn2 plus ions is determined to be that value there. You then have to calculate the rate of production of Fe3 plus ions and water. Also, the rate of consumption of that guy there, and that guy there. So, we are given the rate of production of one product, which is this species here. How do we go about calculating the rate of formation of Fe3 plus and water? These are some guidelines that are used to do this. 1. Make the species to be calculated the subject of the equation. So if you want to calculate the rate of change of Fe2 plus, make the expression for its rate of change the subject of the equation. Put a delta sign there with its concentration represented like that, and delta T at the bottom there. Number 2. Establish a mole ratio by placing the one to be calculated as a numerator and the one that has been calculated as a denominator. So we established a mole ratio here. So we want to calculate iron. We put that as a numerator here, and the one that has been calculated, we leave that as a denominator, and we multiply by the experimentally determined rate. So you can see we're establishing the mole ratio, and you can see you're having 5 moles per liter to 1 mole per liter of that, because the rate of formation of Fe3 plus is 5 times that of Mn2 plus, and that's our answer there. Doing the same thing for water, we make that the subject of the equation, establish our mole ratios, where Water is the numerator. This is the denominator, as usual. And this is the experimentally determined rate at which this is formed. And of course, this is again another way of expressing the mole ratio here, 4 to 1. And that is the rate of formation of water. You can see that the rate of formation in this case is 5 times more than that. In the case for formation of water, it is 4 times more than that there. We'll now be looking at the rate at which permanganate ions are being consumed. Because it is a reactant, and we know that as time goes by, its concentration decreases. To negate any negative charge that might be produced due to change in concentration, be reminded that a negative sign is placed in front of that expression. So again, you make that the subject of the equation. Establish our mole ratio here. And the mole ratio is, according to this equation here, 1 mole of this to 1 mole of that. That's there. That's there. And you multiply, of course, by the experimentally determined rate for this guy, and you can see it's the same. Work out to be the same. Why? It must be the same because you can see that every 1 mole per liter of this is changed whenever 1 mole per liter of that is formed. We now look at the rate of consumption of Fe2 plus ions. Again, make that the subject of the equation. Put a negative sign there. Establish your mole ratio, which is 5 to 1. Make sure that is so. Every 5 moles per liter of that are consumed. For every 1 mole per liter of that is formed. Multiply by the experimentally determined rate for your Mn2 plus ion. Mole ratio is 5 to 1. That's your answer there. Again, doing it for hydrogen. Make that a subject of the equation. Insert that negative sign there. Check out the mole ratio again. Mole ratio is 8 to 1. 8 to 1. Multiplied by the experimentally determined rate for this one here. And you can see that's your answer there. We have another one like this. Similar one to that. According to this equation, iodate ions are reacting with iodide ions in the presence of acid to give you water and iodine. Here you have 1 mole per liter of iodate ions are reacting with 5 moles per liter of iodide ions with 6 moles per liter of hydrogen ions to give you 1 mole per liter of water and 3 moles per liter of iodine. You call it iodine in this country, okay? All right, Guyana, we say iodine. Again, we can use one species to measure the rate of the reaction, and we can use that to calculate the rate of reaction of the others with respect to that one. In this case, the experimentally determined rate of consumption of iodide ions is determined to be this, moles per liter per second. And you're asked to determine the rate of consumption of iodate ions, hydrogen ions, and the rate of formation of water and iodine. Follow the same pattern that we did in the last question. This is how the rate of consumption of iodide ion is being represented. Because it is a reactant, that negative is placed in front of this expression here, and its rate is given, okay? Now we look at the rate of consumption of iodate ions. So what do? You get the expression for iodate ions, delta iodate ion over delta T, but you must put that negative sign in front. And you look at the mole ratio. The mole ratio is, according to this here, is 1 to 5. Let's check it out. Iodate, every 1 mole per liter of this that is consumed, 5 moles per liter of that is consumed. Then make that a numerator. That's always a denominator. Time its experimentally determined rate, and that's what the answer is. Rate of consumption of hydrogen. Make that the subject of the equation. Insert a negative sign there. Establish mole ratio is going to be 6 to 5. Verify that every 6 mole per liter of these are consumed for every 5 moles per liter of that. And you multiply by that rate there, and this is what you get. You can now look at the rate of formation of water. and that's a product, so there's no negative sign. Put your expression there for water. Establish a mole ratio according to this is 1 to 5. Let's check it out, verify that. Only 1 mole per liter of that is produced for every 5 moles per liter of that consumed. So expect it to be 1/5 of that, 1 for 5. That's what it is. Rate of formation of iodine, make that expression the subject of the equation. Insert your mole ratio here. Verify that. 3 of this to 5 of that. That's there too. And multiply by this that belongs to this. And that's what it is. So this is how the rates of formation of different products and the rate of consumption of different reactants can be calculated if the rate of formation of a product is determined or the rate of consumption of a reactant is determined. If you were to plot these values in a graph, if you look at the rate at which permanganate ions, Fe2 plus ions, and hydrogen ions are consumed, and the rate at which Mn2 plus ions, Fe3 plus ions, and water are produced and graphed, you get these following lines here. Of course, you can see here, this one here being a reactant will decline. This one here being a product will increase. These lines here will be similar to that one in terms of decrease and increase. This is being reduced, and that is being formed by the same mole ratio. The rate of decrease of Fe2 plus ions will be exactly the rate at which Fe3 plus ions are increased. And of course, you're going to have water here, which is 4 times that given here. And the guy that is reacting the fastest will be hydrogen, right? You're getting 8 moles per liter for every 1 mole per liter of that guy. You can go back and watch a video again to consolidate your understanding of how if the rate of one species is determined experimentally, then all the rest can be calculated from that.